In November of 2022, the Artemis 1 mission launched out of Cape Kennedy headed to the moon for the first time in over 50 years. The Space Launch System rocket propelled the Orion capsule out of Earth's gravity well and on a trajectory away from Earth.
The SLS, a rocket on par with the powerful Saturn V used in the Apollo missions, is the key to America's return to the lunar surface in the next few years.
Our guest last week was Rick LeBrode, who was the flight director for that mission. Today, we talk with Garry Lyles, who recently retired as the SLS chief engineer at NASA's Marshall Space Flight Center in Huntsville, Alabama.
It really is rocket science, and we'll dig into how NASA engineers manage risks to create the powerful rockets that send humans off the planet. So, Garry, welcome to the Adrenaline Zone. I hate to use a cliche, but Sandra and I have always wanted to have a rocket scientist on the show because this is a show about risk. So, really happy to have you here today.
Yeah, thanks. This is fun. I love talking about rockets. It's one of my favorite things to do.
Yeah, and I'm actually looking forward to getting into the guts of the Space Launch System and the Artemis program with you. But we'd like to start with the beginning of our guest journey. So can you tell our listeners how you got involved in the space sector and what attracted you to rockets specifically?
You know, when you grow up near Huntsville,
yeah.
You're kind of automatically attracted to rockets and NASA. You know, I remember sitting and watching the Apollo 11 landing late at night on TV. My uncle worked for NASA. He was in the facilities office at NASA. My dad worked for a contractor for NASA for a while that did preventive maintenance on the big test stands. And so I got to hear all these stories when he came home about walking to big test stands and the engine tests. I even got to go out to it was kind of an open house back when I was about 10 years old and got to see an engine firing.
Wow.
Those are awesome. Yeah.
Yeah. But, you know, I always wanted to be a mechanic. My dad was a mechanic or a carpenter. My grandfather was a carpenter. So that's what I wanted to do. But my dad would have it no other way than for me to go to school because I was the only one in the family that had ever gone to college. So I decided, well, the best thing for me, if I like mechanical stuff and building stuff, to be an engineer. And but you know, when I graduated, there wasn't much going on. You know, NASA had gone through a reduction in force fairly recently, and they weren't hiring. The only people that were hiring were big chemical companies or steel companies, and I didn't have a lot of interest in that. So I went off to graduate school for a while. And somehow I just turned in a resume to NASA because I was tired of going to school. And I guess, you know, you never know. You can't plan these things the way they happen. Somebody asked me the other day, what would you do if you had, when you were 30 years old, what would you have done different? And I probably would have said, don't worry about planning your life too much because you can't do that. So it just happened to me. I went in, had lunch with a couple of the managers in NASA. They invited me in, interviewed a couple of guys. And suddenly I got a call one day that says, hey, do you want to work for NASA? And they offered me a job. It turns out they offered me a job that I had never interviewed for, didn't know anything about. I walked into a group, the propulsion systems group, that I didn't know anybody, didn't even know what propulsion systems was all about, didn't know what it meant. And it all got started. You know, I sat in the same desk for 10 years doing propulsion and thermal analysis on Space Shuttle.
So, Garry, what was your educational background? That you know, what is it that you think drew you or them to you? Were you a mechanical engineer, chemical?
I was a mechanical engineer. You know, it's one of those things where you look out in the industry and you see who's hiring. And I got into chemical engineering and I hated chemistry.
Yes, good man.
Yeah. So I got into mechanical engineering. Yeah, I have a degree in mechanical engineering.
Gary, I know you worked on the Space Shuttle main engines over there in Huntsville. And I mean, today, they're still the most advanced rocket engines that have ever been built. And it was impressive how well they worked during the Ho shuttle era. We had a few problems with them, but not too many. So what do you think went into making the SSMEs so amazing? And, as we were learning them as operators, it was impressive how fast those turbines were spinning. I don't think people realize that one small failure in those turbine blades would have torn the aft end of the shuttle apart. So why do you think those engines were so successful?
Well, it started with the challenge. Those engines are what they are because of the requirements of the space shuttle. Because it was basically an airplane and the engines had to be relatively small and lightweight. It required a different engine cycle, thermodynamic cycle, than we had ever built before. And that was a staged combustion cycle where all of the fuel that went into that engine went through the main combustion chamber and created thrust. That put tremendous requirements, and because it was a hydrogen engine, it put tremendous requirements on the turbo machinery. And if you remember, there was probably two major advancements in technology with the space shuttle. One was of course, the orbiter tiles, and the other was the high pressure turbo machinery on the space shuttle main engine. So you start with that challenge, and that created a lot of other challenges. We had to do things different than we'd ever done before. We'd always tested components first and then assemble those into an engine system. Well, you can't do that with a staged combustion cycle because the complexity of the test fixture is so much that it's easier just to assemble the engine and put the engine on the test stand. So we started with engine system testing, and the engine, because of its high technology and the turbo machinery, had a lot of problems in the early days. It had rotor dynamic issues. It had thermal issues. We cracked turbine blades. But how we got there was a lot of test. We went through what we used to call a test, fail, fix cycle, where we had to test and find the problems and fix the problems and go into test again as rapidly as we could. It turned out that the more we tested, better we got, the more design changes we made. We evolved that engine, though, over time significantly with new turbo machinery.
So what lessons did you learn working with the SSMEs that were useful for the design and manufacture of SLS? Because I don't think a lot of people realize that the engines that are going to be long-term on the Space Launch System are derivations of the Space Shuttle main engines.
One lesson I learned in working the SSME Space Shuttle main engines was the process of evolution. There's nothing that can compete with the process of improvement, test, improvement, test, improvement. I led a team of rocket engineers that came from the three existing rocket engine companies at the time, which was Rocketdyne and Pratt & Whitney and Aerojet. And what I learned from that is we looked not only at rocket engines, but at airline engines and fighter jet engines. And we found out that they were unbelievably reliable. They operated at temperatures as high as the Space Shuttle main engine, not at the pressures, but they still were under high stress, high energy operation, and those engines would run forever. And it was because they had evolved those engines over time and kept improving them. And they had a what they called a technology test bed at all of the engine builders, and they would run all of their technologies through that technology test bed ground test engine before they ever incorporated it into the engines. That led me to believe that the next vehicle should not be a leap in technology if we wanted to actually implement it within the cost ceiling that we had and within the schedule that we wanted to advance a heavy lift launch vehicle. So all of that learning about evolution led me to believe that we ought to evolve into SLS. And that's the reason we have the propulsion system we do. That's the reason we have RS-25s, which is the Space Shuttle engine, basically. That's the reason we have the solid rocket boosters, because I avoided much of the risk of development by utilizing the propulsion system that had evolved over time. And we'd already invested all of this learning into that propulsion system.
So, Garry, got a couple questions for you. One, I got to ask, I know it had to be a real thrill for you the first time you saw the shuttle launch and do it safely, because, your rocket engine was on that thing. But as an engineer, as a design and test engineer, it probably was almost equally important to you the first time you ran that engine on a stand and it did what you wanted it to do. It was, the test failed test. It was like actually a successful test. This thing's ready to go. Which of those moments was more special for you?
I think seeing the flight, I never will forget STS-1. It was the most beautiful thing I'd ever seen at the time, because when it cleared the tower and did the pirouette to fly east, I thought it was the prettiest thing I'd ever seen. Mm-hmm. And I guess I still do. SLS rivals it. SLS produces more power and more noise, and it looked like the sun rising that night. But I never will forget the shuttle launch.
Yeah, and a shameless plug here. I believe John Young was the commander of that mission, former Navy pilot and Georgia Tech graduate. So a little intersection here with that. So let's talk about Artemis a little bit. For our listeners, NASA's most recent big kahuna rocket, right? Can you put that system in context for us? How big is it compared to, say, the rocket that launched the Apollo missions to the moon? Can you give us a sense for the size?
It's comparable to the Saturn V. We actually produce more thrust than Saturn V. We're up above 8 million pounds of thrust. It's certainly a different looking vehicle. In its evolved, in its final configuration, it will be very similar to the payload capability of Saturn V.
The Artemis 1 launch buildup went through several attempts, and I know people were watching in the news and sort of trying to figure out what was going on. So you can walk everybody through why that happened and how you had to manage the risk and unknowns of dealing with the first time launch, because you were learning every launch attempt. There was a new learning point, right?
We knew a lot about the vehicle because we had taken the core stage and engines through the green run test, and we haven't had a lot of experience with the propulsion system. We had test fired the solid rocket boosters many times. What is different is when you go to a new facility. I always worry about interfaces where the facility and the vehicle are joined together, and you have to operate them as one system. And that being the brand new thing about the first launch. There's always learning involved, especially with, I say especially, it's any vehicle, but with hydrogen vehicles, it becomes very important to have good interfaces.
Yeah.
Because hydrogen likes to leak, right?
Hydrogen
Little tiny
loves to leak. Yeah. Yeah, that's what makes it such a good propellant. And so you have to deal with operational problems that it creates. But what we found in doing that, and so we planned on tanking test, a wet dress rehearsal. We had planned to do whatever it takes to get the loading procedure correct. And those are the kinds of things that we had to work. It's not surprising that we had to do it that many times. My experience with shuttle is the launch vehicle had many more problems than SLS had on the first space shuttle flight. But again, those interfaces create problems. And so in this case, the first launch attempt, we could not show, based on the criteria that we had set, using the instrumentation that we had available to us, that one of the engines had actually been chilled down to the point that it could get in its start configuration. That was probably due to the constraint we put on it, because and this is what was nice about the first attempt was we didn't really, we had the opportunity when we couldn't chill the engine to actually go through troubleshooting on the pad. And so that first launch attempt became a test for us. And we reconfigured the vehicle and ran several tests, including closing off all of the engines except the one that we couldn't prove that we had chilled down. And we showed that engine was actually chilled appropriately. And so we changed our criteria through a lot of past experience with that engine. We knew it was being chilled. The next attempt, we had a leak. We had also had a leak on some of the fill and drain valves and fill and drain disconnects, and we could not show. This is a case where you have a criteria again that limits the amount of hydrogen that you can leak, and we could not. We kept breaking that limit. And so it created a situation where we actually had to roll back, replace some of the seals. We actually, in real time, changed the loading procedure on the hydrogen side, because we determined that we were trying to load hydrogen too fast, and it was not allowing that seal to position itself and seal. And so the crew changed the loading procedure. They called it a softer, gentler loading procedure. But all that was done. All that learning happened, and it's things that's almost normal. You have to go through. We won't go through that kind of thing again. But we may have leaks again. But that was a great learning process, that first launch.
One of the things I was just going to say, one of the things I try to remember, is, this nation does a lot of things that are very technically difficult. And we're usually the first nation to do it. And they're very hard. Things like, the V-22, things like stealth technology. And so it may be embarrassing in the media, but in fact, there's nobody else who can do this kind of stuff. And we always try to do it as safely as we can. So, And
if I can, for our listeners, Garry was talking about constraints. And so when we are dealing with a complex system for the first time, the engineering team and the operations team sit down and they write down a list of sort of parameters that they know are really important to manage the process safely that they don't want to exceed. And so if during the process, some of those parameters get exceeded, then they know to stop. And that's, Garry, what you were talking about with this engine situation.
So, Garry, let's talk a little bit about the design team. In my humble aerospace engineering education, I was always struck by the trade-offs that are there. You know, the structures folks always want the beefiest, strongest structure, which costs weight. You know, the aerodynamics folks always want the slickest, cleanest, you know, exterior of, in the right shape and all that. And of course, the propulsion people are stuck in the middle. And everybody's fighting against drag and weight and lift and all that sort of stuff. You know, I'm familiar with that with airplanes, but what about, designing a rocket? What kind of trade-offs do you find from your side of the house as the propulsion person? How does that process work when you're doing a rocket instead of an airplane?
I think it works very similarly. The big job of the chief engineer, really, as the architect of the design, is to manage all of those trades. We had a unique situation with SLS in that we had existing designs that we were integrating with one clean sheet system, which was the core stage. When you have a situation where your engines, your boosters, your upper stage, even your spacecraft was already designed, you don't only have trade-offs, you got an integration job of making sure that you don't impact an existing design and cause them to change unless you completely have to do that. We have, for example, more thrust going through the going through the forward attach of the boosters on SLS than we had on Space Shuttle. And to keep from redesigning that forward attach, we put the forward attach into a structural test so that we tested it all the way to failure to see what its actual margin of safety was. And so the trade-off was, okay, depend on your analysis and redesign the forward attach, or go spend some money on a test article and break it, and see what kind of margin of safety you have. Those kind of trades were, I think, unique to SLS because of the way we had to deal with the existing designs.
It sounds like what you're saying in that very interesting example of testing to failure rather than redesigning, that you must have found that the original design was more conservative than they thought, because if it had failed exactly where they thought it was going to fail, you might not have been able to use it.
Yeah, we did. We found out we had a sufficient safety margin, and we normally find that out. That engineers are relatively conservative.
Yeah.
And so you have to really push back. Everybody wants to carry a little bit of margin in their pocket. And my job as the chief engineer was find it. Let's find that margin. Let's get it all out on the table and see what we have, because we can't afford, for launch vehicles, you can't afford heavy. You just, the rocket equation doesn't allow it. You want as much specific impulse as you can get, and you want as light a weight as you can get. That becomes a problem with a hydrogen system. One of the early trades that we made, should I go with hydrogen or should I go back to the Saturn V kind of configuration with a heavy propellant? And a trade always gets to be, can I build a hydrogen tank, propellant tank that big? And is it going to be light enough that I can that it actually will be provide me with the performance that I need? When we made those trades, we knew that we were trading some manufacturing difficulties with SLS that we would not have had with a heavy propellant. So what I had to trade in that case was, do I want to develop a new rocket engine or redevelop a F1 Saturn engine from 50 years ago knowledge, or do I want to develop a kerosene or a heavy propellant engine from scratch, or do I want to reduce the risk on the propulsion system and take the risk in the manufacturing process on the hydrogen tank? And that's an example of a trade.
So, let's talk about that for a second, because there were some challenges with manufacturing that tank, as a matter of fact. And NASA had to go back, and the contractors had to go back and look at the friction stir welding process and how you scale it up. Did you guys have other manufacturing issues, and how does that affect risk and safety?
You force it not to affect risk and safety.
Yeah.
You try to force those kind of issues into the schedule risk, and cost risk, and out of the safety risk, and so that's what we do. One of the big manufacturing issues was the size of the tank. We had to build a welding machine, a friction stir welding machine, the size that had never been built before. We had to weld because of the loads that go into the LOX tank. We had to friction stir weld a weld that was thicker than we had ever welded before. And so we had to develop all of those welding criteria, the speed of the RPMs of the friction stir welder, the speed of travel. All of those things had to be developed basically from scratch. And we had the alignment of the welding machine had to be unbelievably close, and we had to fix that a couple of times. Yeah. The inner tank is required to take so much load that it is a heavy formed structure that it is riveted together or bolted together. And we had a lot of problems assembling that inner tank area that carries all of the thrust of the solid rocket boosters. It was mostly the size, the fact that we had to train a new manufacturing crew that had to build hardware that had never been built before. It turned out that manufacturing was the long pole in the tent, basically, when it came right down to SLS.
So I've always been curious, how would you describe the differences in design and manufacturing approaches between design, when you're working on a crewed vehicle versus an uncrewed vehicle? Is it margins mainly?
Yeah, well, yes, that's one of them. It starts with the design, and obviously I've never worked on anything but human-rated vehicles. So I don't necessarily know what kind of additional risk might be taken in a non-crewed vehicle. If I was designing a non-crewed vehicle, I would put a lot of the same design specifications in it as I would a crewed vehicle, because it drives you to reliability. And if I want a highly reliable launch vehicle and not lose a very expensive or maybe a one-of-a-kind payload, then I want a highly reliable vehicle. And that starts with design criteria. We have design standards that sets factors of safety on stress. It sets factors of safety on fatigue life, both low cycle and high cycle fatigue. It also sets some criteria on redundancy. There's a lot of systems that, especially in avionics systems, electrical components, where it's very easy to add redundancy to the system. And so you look at fault tolerance. I would like my system to be at least one fault tolerance and most times two fault tolerant. Those all go into the selection of the electrical components. For example, you want to have the paperwork and the testing and the proven reliability on those components. And then in many cases, you still have redundancy. We have redundancy in our computers. We have redundancy in all of our operating instrumentation, which allows us to assure that we don't, for example, shut down a good engine. So all of those things go into the design. Plus, you got to remember that the crew is an asset, and so we
Thank
have.
you.
If you've got a crew on board that can prevent a failure, then you want to be able to use the crew to do that. It works better in an in-space situation where things are happening slower. It's hard to do on a launch vehicle.
Yeah.
But for example, on this launch vehicle, we have provided the crew with the ability to change the guidance if they need to, and so they can actually enter into the flight software, and they don't have a stick that they can fly the vehicle with, but they can enter and input into that configuration.
So Garry, if I may interrupt real quick, just this is because with AI coming on and computers getting more and more, I guess I don't say the word intelligent, I guess but adaptable to unique situations. How long do you think that the crew is going to be as much of as an asset for that purpose as you just talked about?
I think as long as we have pilots for crew.
Thank you. As he throws his white scarf over his shoulder. Okay.
I just had to ask that question.
We'll never get there. We always have one difference in the design process on a crewed vehicle is you got the crew involved.
Yeah. And
so, all the crew sits in all of our meetings. We talk to the crew all the time. We understand what they want. And I asked one of our crew members one time, "You're never going to give up on having the capability to fly this thing, are you?" And he said, "No." And I said, "Okay, I give up then. We will do that."
Sorry, I had to ask.
The other important thing is, as a last resort, if I have one or two failures and I have an imminent catastrophe, then I need a way to get the crew off. And so having a launch abort system and the ability to send the crew caution and warning from the launch vehicle to tell them what the status is of the vehicle and to recommend abort if the vehicle thinks they need to get off. All of that, you just don't have that in an uncrewed vehicle, and so that's a design parameter that you have to deal with. You don't want abort regions where you have what we call black regions, where there's no place to abort. In the case of SLS, if we lose an engine, for example, which I don't expect, but if we lose an engine on the pad, we can take Orion to a nice, safe location to get off. They don't have to get off right then and do some kind of miraculous abort.
And if I may, I don't think people realize that we had black zones on the shuttle, and we had some very sporty abort scenarios right off the pad that.
I remember the crew, including John Young, talking about the RTLS.
Yeah, return to launch site.
Return to launch site, and that was sporty.
I would never have wanted to fly one of those.
We'll probably get into that when someday we interview Sandy, and she can tell us all about the things that we didn't know were happening.
But anyways.
Yeah. So hey, we're getting close to being out of time. I did want to ask you, Garry, about the future of rocket design. There are a number of applications in space for rockets that don't rely so much on chemical reactions, for example, like which prevents you from having to carry a lot of heavy fuel. Things like electrical power to accelerate xenon ions to very high speeds. That sort of thing. What do you see? Not just for the sort of maneuvering and control little things, but for the big things. Are there any major technologies coming down the road that could fundamentally change the business of putting heavy objects into space, or are we pretty much stuck with what we've got?
It is hard to beat hydrogen combustion. When you want to go take heavy things very fast, you're taking me back to some years that I spent managing what we call advanced propulsion. And we thought of all kinds of things. We thought about lasers, laser propulsion to shoot the vehicle into space. We thought about augmenting the lift off with a magnetic rail, for example, to get it up to speed so that you don't have to carry the big boosters. One of the big technologies that we spent a lot of effort on that is still out there is air breathing combined cycle propulsion. We had the National Aerospace Plane program back in the early 90s. We had X-33 and Venture Star in the 90s. Single stage to orbit is still, you got combustion, but you're leaving one propellant on the ground. You're breathing air. I think combined cycle going to hypersonic propulsion is one of those things that will eventually happen. We took it on earlier than we should have. We were a little bit optimistic about how lightweight we could make a vehicle, what kind of thermal protection we would need because we're traveling through the atmosphere at Mach 7 or 8 or whatever it turns out to be. All of those technologies will come along someday. I think the nearest term non-combustion kind of technology, though, will be nuclear propulsion.
Mm-hmm.
And I think if we've really got our mind on Mars, and we don't want to spend forever in cislunar space, if we really want to go outbound into the solar system and beyond, I'm a believer that nuclear propulsion or a hybrid of solar electric propulsion and nuclear propulsion will be what gets us to Mars.
Interesting.
The nuclear is getting a fresh look. I saw Pam, who's our listeners, the deputy administrator of NASA, announce that NASA and DARPA is going to work on a nuclear program for engines.
I'm happy about that. I'm really an advocate because, we've done, Moon is hard. Mars is an order of magnitude harder. And if we really, the big deal with Mars is if we want to protect the crew, limit the radiation environment, and actually take people to Mars, we've got to get there as fast as we can. Now, I'm all for taking cargo and pre-placing resources on Mars with solar electric or anything we can. It can be a slow boat, but I would be for putting the crew on the nuclear system and getting them there as fast as we can. Plus, you can go anytime with the nuclear system. You don't have to wait for the 2-year cycle.
When the planets align.
You have to wait for the planets to be aligned. Otherwise, with nuclear system, you got so much performance, you can go direct.
Yeah. Well, maybe we'll see it in our lifetime. And as we wrap up, Garry, first of all, thank you for your time. Secondly, congratulations to you and the whole team. The Artemis 1 launch was flawless. And we heard a little bit today about all of the, behind the scenes work that goes into making it look so easy. And it's not. We look forward to Artemis 2, 3, 4, 5, and beyond as NASA continues its campaign to develop some cislunar activities in preparation for Mars. So I think you can be very proud of you and your team and what you guys did to put us on that path. And it was just delightful talking with you today.
Yeah, it's great to cut through the media and all that kind of stuff and talk to somebody who really has their hands on it. It's really fun. So thanks.
Well, thanks for inviting me. Like I said, you could take either one of those subjects, and I could talk an hour on. So I'm sorry if I went long-winded, but I would like to say that I am very proud of the team. This was a great design and operations team that we put together over the last 10 years, and I'm very proud of them and happy for them.
Well, good.
As you should.
And we wish you and that team continued success.
Thank you.
That was Garry Lyles, former NASA chief engineer of the Space Launch System rocket. I'm Sandra Magnus.
And I'm Sandy Winnefeld. Join us next time for another episode of The Adrenaline Zone.